Hi, this is Osama Amrani from grade 9 at Al Nahda School in Sana'a, Yemen. Today I will talk about the periodic table. Ever wondered why the periodic table looks like a strange game of Tetris with a lot of squares filled with letters and numbers? Well, it's not just a random collection of symbols, but a systematic arrangement of the elements that make up our universe. It's a little like the ultimate cheat sheet for chemists, physicists, and anyone interested in understanding the building blocks of life. At first glance, the periodic table may seem a bit overwhelming, but once you get the hang of it, it's actually pretty straightforward. The table is organized based on atomic number, electron configuration, and recurring chemical properties. Atomic number, you ask? It's simply the number of protons in an atom's nucleus. As for electron configuration, it's all about the arrangement of electrons around the nucleus. Now let's take a closer look at how the table is laid out. The elements are organized into rows and columns, known as periods and groups, respectively. The periods, or horizontal rows, indicate the energy level of an atom's outermost electrons. As you move from left to right across a period, the atomic number increases, which means the number of protons and electrons also increases. On the other hand, the groups, or vertical columns, are where things get really interesting. Elements in the same group share similar chemical properties, because they have the same number of electrons in their outermost shell. This is why, for instance, all the noble gases are in the same group. They're all quite happy with their electron arrangement and generally don't react with other elements. So, the periodic table is essentially a map guiding us through the vast landscape of elements, from the lightest hydrogen to the heaviest oganesson. It's a testament to our human curiosity and desire to categorize and understand the world around us. The beauty of the periodic table lies in its organized chaos, each element with its unique characteristics, yet collectively forming a harmonious whole. Now imagine a group of elements so reactive that they aggressively react with water. Welcome to Group 1, the alkali metals. These metals, comprising elements such as lithium, sodium, and potassium, are known for their high reactivity. The reason behind this is quite fascinating. You see, alkali metals possess a single electron in their outermost shell, a characteristic that makes them eager to participate in chemical reactions. Take lithium, for instance. It's the lightest of all metals and floats on water, only to react with it vigorously. Sodium, on the other hand, is a critical component of our daily diet. It's a major part of table salt and plays a vital role in our body's fluid balance. Then there's potassium, another essential dietary element that's crucial for the functioning of our heart and muscles. So next time you sprinkle some salt, remember it contains an alkali metal, sodium. Moving one step to the right, we meet the alkaline earth metals of Group 2. These metals are a fascinating bunch, slightly less reactive than their neighbors on the left, yet still full of surprises. Let's dive into the specifics. We start with beryllium, the lightweight of the group, known for its exceptional stiffness and stability. Next, we have magnesium, a star in its own right. It's not just the stuff of fireworks, but also crucial for photosynthesis in plants. Who knew? Then we encounter calcium, a household name, recognized for its role in building strong bones and teeth. But did you know it's also a key player in cement production, and even in the making of cheese? From beryllium's stability to magnesium's role in photosynthesis and calcium's part in construction and dairy, the alkaline earth metals of Group 2 are versatile and vital. From strengthening your bones to sparking a fire, these elements are more common in your daily life than you might think. Now prepare to enter the bustling metropolis of the periodic table, the transition metals. These are the elements that live in the middle of the periodic table, in groups 3 to 12. They're the life and soul of the party, always changing, always adapting, and always surprising us with their unique properties. Transition metals are the chameleons of the periodic table, capable of changing their valence or charge to form compounds of various vivid colors. Imagine a world devoid of color. Dull, isn't it? But thankfully, we have transition metals to thank for some of the most vibrant hues we see around us. From the rich blue of a copper sulfate solution to the intense red of iron oxide, these elements bring a splash of color to our world. But their talents don't stop with color. Transition metals are incredibly versatile, and their properties make them invaluable in construction and manufacturing. They're hard, durable, and have high melting and boiling points, which makes them perfect for building everything from bridges to skyscrapers. Now let's meet some of the stars of this bustling metropolis. First up, we have iron, or Fe, as it's known in the periodic table. This hardy element is the backbone of our modern world. It's in the cars we drive, the buildings we live and work in, and even in the hemoglobin that carries oxygen around our bodies. Next, we have copper, or Cu. This element is a master of conductivity, making it essential for electrical wiring and electronics. And let's not forget its role in creating beautiful green statues like the Statue of Liberty. Finally, we have gold, or Au. This element needs no introduction. Its beauty and rarity have made it a symbol of wealth and power for thousands of years. It's in the jewelry we wear, the awards we strive for, and even in the circuitry of the devices we can't live without. So, from the golden ring on your finger to the iron in your car, you're surrounded by transition metals. As we venture further to the right of the periodic table, we encounter the non-metals and the noble gases. Non-metals are a diverse bunch. They're like the eccentric cousins at a family gathering. They can be brittle solids, liquids, or even colorless gases. Their physical properties are as varied as their appearances. For example, carbon, a key player in life as we know it, is a non-metal that can appear as soft graphite in your pencil or as a hard diamond in your jewelry. Then we have oxygen, another non-metal, and a vital one at that. It's the breath of life, quite literally. About 1/5 of our atmosphere is made up of this colorless, odorless gas. It's essential for our survival and for the survival of most life forms on Earth. Oxygen is always ready to react, forming compounds with almost all other elements. This makes it a bit of a social butterfly in the chemical world. But not all non-metals are as reactive as oxygen. Some are quite happy being left alone, like the noble gases. This group of elements, which includes helium, neon, and argon, are the introverts of the periodic table. They're stable, thanks to their full electron shells, and they don't readily form compounds with other elements. Take neon, for example. It's a colorless, odorless, tasteless noble gas, but when electricity is passed through it, it lights up with a brilliant red-orange glow. You've probably seen this in neon signs around the city. Neon is unreactive, content in its solitude, but it sure knows how to light up a room when it wants to. The non-metals and noble gases are our constant companions. They're in the air we breathe, the water we drink, the earth beneath our feet, and the lights that guide us through the night. They may not be as flashy as the metals, but their diverse properties and behaviors make them just as fascinating. Whether it's the air you breathe or the neon lights in the city, non-metals and noble gases are omnipresent. The periodic table, a seemingly daunting labyrinth, now hopefully seems a little less mysterious. Through our journey, we've explored its structure, its organization, and the unique characteristics of each group of elements. We began by unveiling the periodic table, a map of the building blocks of the universe. Each element, each atom, has a place, a home within its rows and columns. We learned that it's not just a random assortment of letters and numbers, but a carefully structured catalogue, ordered by atomic number and divided into groups based on shared properties. Next, we delved into the alkali metals, the residents of Group 1. They're a lively bunch, known for their reactivity and their willingness to lose an electron in the name of a stable outer shell. They're the kind of elements that just can't resist reacting, especially with water. Then we moved on to the alkaline earth metals, Group 2. Just like their neighbors, they're reactive, but a bit less dramatic. They're the steady ones, always ready to lose 2 electrons to achieve that perfect outer shell. We traveled through the bustling city of transition metals, Groups 3 to 12. They're the versatile ones, the multitaskers, capable of forming compounds in many different ways. They're the color bringers, the catalysts, and the sturdy backbone of many materials we use every day. Finally, we ventured into the realm of non-metals and noble gases, Groups 13 to 18. They're the diverse crowd, ranging from life-sustaining oxygen to unreactive neon. Some are eager to gain electrons, others are content with their full outer shells. And there we have it, a whirlwind tour of the periodic table. From the reactive metals to the diverse non-metals, each element tells a story, each group a chapter in the grand narrative of the universe. Remember, the periodic table isn't just a chart, it's a story of the universe, written in atomic letters,